Hi everybody. In this session, we will discuss concepts of electric charges and fields, electrostatic potential and capacitance. First, electric charges and fields contains these subtopics: electric charge, conductors, insulators, basic properties of charge, Coulomb's law, electric field, field lines, dipole, continuous charge distribution related field, and Gauss law. So majorly Coulomb's law, Gauss law, their advantages, limitations, and all those things. Electric charge. Charge is a fundamental property and its value can be plus or minus 1.6 into 10 to the power of minus 19 coulombs is the least possible charge. Least possible charge is 1.6 into 10 to the power of minus 19 coulombs. And charge of proton is positive, charge of electron is negative. That only the least possible charge, right, outside the atom or the nucleus. Next, properties of charges. Like charges repel, unlike charges attract. Total charge of an isolated system is maintained constant and charge is quantized. It's a scalar quantity. Charge won't exist as a fraction of electron charge. Charge always exists as an integral multiples of charge, and charge can be transferred from one body to another body and it obeys conservative laws. And frictional electricity is nothing but types of methods of making bodies charged. That is, friction is one of the methods. By rubbing with one body with another one, then electrons can be transferred easily from one body to another body. Nuclei transfer is difficult, electron transfer is easy. One you can memorize in the mind, that is, if you rub a silk cloth against a glass rod will become positive, silk cloth will be negative. Reverse, fur cloth and an ebonite rod. Reverse. Memorize only one. Glass rod, silk cloth. Glass rod becomes positive, silk cloth becomes negative. Enough. Next, charge is invariant. Charge is invariant means if a body is moving comparative to light velocity, then body's mass will change, body's dimension will change. That is called length contraction, mass enhancement, time dilation. These are all relativistic things, but charge will be same even though it's at rest or in motion. And charge cannot exist without mass. Very important point. Charge cannot exist without mass. Photons are not having mass. Therefore, they can't have charge. So, the photons contained by light cannot be deviated by electric magnetic fields because they are not charged. Next, quantization of electric charge. Of course, any integral multiples of charge of electron. And next, Coulomb's law. Every charge getting attracted or repelled by another charge. So that force F is proportional to Q1 Q2 by R square. F is equal to constant, that is medium constant Q1 Q2 by R square. K is given by 1 by 4 pi epsilon naught for free space, and for any other medium 1 by 4 pi epsilon. See, the value depends upon unit system and medium. SI system, K value 1 by 4 pi epsilon naught. For free space, its value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. And CGS, K value totally we will take as 1. And mu epsilon naught is permittivity of the free space, 8.85 into 10 to the power of minus 12. And force on first body equal to force on the second body. They form action-reaction pair. One is in one direction, other one is in opposite direction. They contains equal magnitude of force. See, force on large charge is not smaller than force on smaller charge. Actually, force on small or large, force on one body equal to force on the other body. That is the thing here. And Q1, Q2 greater than 0, the force is repulsive. That means like charges. And Q1, Q2 less than 0, the force is attractive. And this Coulombic force is a central force, is a conservative force, always unidirectional. This force is between two charges independent of presence of other charges. Two charges can be dealt separately. If the Coulombian force acting between two charges is mutually interactive, the force acting between two charges is equal to magnitude and opposite in direction. The ratio of electric force between Q1 and Q2 is 1:1. Coulomb's law is applicable for the distance more than 10 power minus 15 meter, and it can be applied for the point charges only. Charge Q is divided into two parts such that the force between them is maximum. Then those charges must be equal, and that means the divided two parts must be equal. So Q by 2 only. And to have same force at different distances, then you need to have this relation F1 R1 square equal to F2 R2 square. Force in medium, if having dielectric constant K1 and force F1 is in dielectric constant K2 and experiencing same forces, then the distances should follow this one. And at the same distance, if you want, then F1 K1 is equal to F2 K2. If two identical spheres carry charge Q1 and Q2 and force acting between them is F dash, they are brought in contact and then separated back to the same distance, then F dash is equal to Q1 plus Q2 square by 4 Q1 Q2 into F. And Coulomb's law in vector form, F12 is equal to my same expression minus 1 by 4 pi epsilon at Q1 Q2 by x square into I cap, because F1 will act force this way, F2 will act force that way. So we'll have force that way. So that way, that's why F2 will have positive sign and F1 will have negative sign. That is somewhat important thing. And relative permittivity, nothing but dielectric constant. Relative permittivity is permittivity of the medium by permittivity of free space. Relative permittivity also known as dielectric constant. So K equal to epsilon R equal to epsilon by epsilon naught. Coulomb's law in terms of dielectric constant K, when two charges are put in medium, the electric force between them is Fm is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. And epsilon by epsilon naught is K. So you can, force in a medium is 1 by 4 pi epsilon naught into K by into F1 Q1 Q2 by R square. Therefore Fm is equal to F by K. Here only I would like to write the other things also, because it's a good point. I can add some other things here, that is electric field E is equal to E naught by K, potential V is equal to V naught by K, capacity C equal to Kc naught, because epsilon naught will be in the numerator for it. And see, 1, 2, 3, 4, all the 4 you can have at one place. If the charges are placed in a medium, then free space one and medium ones are related like this. And for an insulator, K value is greater than 1, insulator K value greater than 1, and for a vacuum K is equal to 1, K is equal to 1. Air and vacuum we usually consider the same because very small differences, and conductor's K value is infinity. According to law of parallelogram, the resultant force on charge due to two charges is square root of F1 square plus F2 square plus 2F1 F2 cos theta, and theta is the angle between F1 and F2. So whenever two charges are there, then the resultant force due to the two charges forces can be obtained like this. And multiple charges you can apply. For application of parallelogram law for multiple charges is difficult but not impossible. The space around the region under the influence of a charge is known as electric field, and electric field intensity is the force experienced by a unit charge in the field at a given point. That is and here I want to say, we use a test charge. Test charge always a positive charge and a small in magnitude, that only treated as a test charge. And electric field intensity units is Newton per Coulomb or volt per meter. It is a vector quantity. Its formula is E is equal to F by Q, or F equal to EQ or QE. According to Newton's second law, this force can cause an acceleration in the test charge. F is equal to ma, A is equal to F by m, EQ by m. And charge is in motion in electric field, then velocity after t is given by V is equal to U plus AT. A can be taken as EQ by t, EQ by m into t. So all the equations is going to follow as usual, but just acceleration you replace with G must be replaced with EQ by m. Even gravitational equations also you can use, whatever is related. Electric field due to a point charge, electric field due to a point charge, that is equal to 1 by 4 pi epsilon naught Q by R square, and in which direction force is, that direction only field direction. E is equal to 1 by 4 pi epsilon naught Q by R square. Pointer also visible in its visibility also good. Why? Because it's in white in color, right? That's why. So here are some cases for different things. What are these? Two equal charges, then at the midpoint electric field will be 0. Three identical charges are forming an equilateral triangle, then at centroid field will be 0. Four charges, then at the center, geometric center, field will be 0. And 6 charges, then at geometric center field will be 0. And the fifth one, pentagon, even then also at the geometric center field will be 0. electric lines of forces. In other cases, field will not be zero. Electric lines of forces. These are imaginary lines whose tangent will give you electric field direction in a space. So electric lines of forces are emerging rays from positive charge and converging lines at a negative charge. They converge and they diverge. Diverge from a positive charge, converge at a negative charge. And two identical charges if you have, they will come like this. This is fourth one is two identical charges, and dipole will give you lines of forces like this. Even these pictures also asked in competitive examinations many times. Properties of electric lines of forces. They come out of positive charge. Of course, whatever we discussed, those only will be. And no lines of forces will intersect. That is one of the important. And this pattern. You think these patterns? Following patterns of lines of force are not possible. These patterns not possible. Intersection not possible. Looping not possible. And this is also one type of intersection not possible. And so next, a system of two equal and opposite charges separated by a distance, two opposite charges, and then they form a dipole because they are unlike charges. Unlike charges separated by certain distance will call as a dipole. Dipole moment is given by P. P is equal to 2a into q. 2a is because from center to one of the charge is plus a and one of the charge is another a. So total 2a. 2a into q is known as dipole moment. Next, units. The most practical example of a dipole is a water molecule and its unit is coulomb meter. Water is a dipolar compound, right? Ideal dipole. An ideal dipole is a short dipole whose large value of q with a large value of q and negligible value of 2a. That is a ideal dipole. And dB, unit of dipole moment is dB for an electron and proton separated by 1 angstrom distance. Electric field due to an electric dipole on the equatorial line and axial line at an intermediate positions we are going to discuss here. See, 2pd or 2pr, whatever is suitable for you, that only you no need to change your memory aids. 2pd by 4 pi epsilon naught d square minus a square whole square. I know with d only, here it is r, no issue. And if it is on the axial line, dipole say axial line. If it is a short dipole, then if it is short dipole, a square in addition and subtraction can be neglected. So it will be 2pd, 2pd gets cancelled now, that's why 2p by 4 pi epsilon naught into d cube or r cube. On equatorial line, minus p by 4 pi epsilon naught r square plus a square whole power 3 by 2. On making a square 0 due to small dipole, you will get just p by r cube. This is p by r cube, this is 2p by r cube. Minus sign indicates opposite direction. For an ideal dipole, r square plus a square is equal to r square because size distance between two charges is negligible. And for an ideal dipole, E equatorial is equal to E axial by 2. And E net is equal to, at any other point called polar coordinates r comma theta, then electric field is given by 1 by 4 pi epsilon at p by r cube for root over 1 plus 3 cos square theta. You need to know all these formulae. And tan alpha is equal to, that means the resultant direction of resultant field with the axis of the dipole is EQ by E axial, E equatorial by E axial, that is half tan alpha. Tan alpha is equal to half tan theta. Tan alpha is equal to half tan theta. This is also important thing. In JEE model questions, we have this type of questions. When E is perpendicular to P, then alpha plus theta equal to 90 degrees and theta equal to tan inverse root 2. Electric dipole placed in a uniform electric field will experience a torque. Not in all the directions, one particular direction it won't have torque, in other directions it will have torque. The torque experience having the formula that is equal to, here he gave electric field direction and dipole direction is in the same direction, parallel. P bar is parallel to E bar, in opposite direction this one. In opposite direction net force, parallel direction net force 0 only, but whereas torques will be different. That torques we are going to see. Torque is 0 in parallel direction and net torque is 0 in this case also, and remaining two cases we are going to discuss. That is, net force is 0 in any other case, but torque is equal to PE. Torque is equal to PE. Case 3, when P is perpendicular to E. Case 4, P makes an angle theta. That is PE sin theta. PE sin theta, not QE. PE sin theta. This is QE sin theta. That is P bar cross E bar, correct only. P bar cross E bar is correct only. This is generalized thing. Why should we learn so many formulae? We can use this one. Torque tau is equal to torque tau is equal to P bar cross E bar. P bar cross E bar. So it is PE sin theta, where theta is the angle between E bar and P bar. Potential energy of a dipole in an external electric field. Potential energy of a dipole is nothing but work done in rotating from theta 1 to theta 2. Whatever will be stored in it is the potential energy. First work done, W equal to minus PE cos theta 2 minus cos theta 1. Simply people will write PE cos theta 1 minus cos theta 2, taking this minus inside. And change in potential energy will be this work done only. So potential energy will be minus PE cos theta. Potential energy minus PE cos theta. Work done is this one. Next, electric flux. Number of lines of forces that are passing through a given area is known as electric flux. Electric flux is phi. It is represented as E bar dot A bar. This is a dot product of two vectors. It's a scalar quantity. So phi is equal to integral E bar dot dA bar also we can take. That is also dA EA cos theta will come. And flux units also important. Flux units are voltmeter. Voltmeter is the unit of flux. Voltmeter. Next. These are all flux. Whenever E is parallel to A, maximum flux. E perpendicular to A, zero flux. See, flux is useful if and only if it is passing through the area, or if it is passing over the area is useless. If it is making an angle theta, then EA cos theta you have to consider. Oh, many cases I gave. Very good. Next. Total electric flux through an enclosed surface is equal to 1 by epsilon naught times of the charge present in it. So phi is equal to emerging flux, total emerging flux, phi is equal to sigma q by epsilon naught, whatever the charge present in the closed surface. That is called Gaussian surface. And different things. For the first Gaussian surface, charge is present inside, that is q by epsilon naught. Second one, charge is not there in the surface, so total flux is 0. In the third one, we have Gaussian surface inside, so there is q by epsilon naught. And for the fourth one, total, this is dipole is embedded in a Gaussian surface, so net will be 0 in the fourth one. Applications of Gauss law. For a sphere of charge, you can have r greater than r, that is outside point. Outside point q by 4 pi epsilon naught r square for a charged conducting sphere or a shell. So E is equal to q by 4 pi epsilon naught r square. On the surface, capital R square will come, and inside will be 0. Inside field will be 0. And the graph related to electric field and the distance for a shell or a conducting sphere is like this. Inside field is 0, outside it is inversely proportional to 1 by r square, maximum on the surface. Next, this is a non-conducting sphere. Non-conducting sphere, field inside of course uniformly charged. Field inside is directly proportional to r and outside is inversely proportional to 1 by r square. Maximum is on the surface, and field inside will have the formula qr by 4 pi epsilon naught r cube. Qr by 4 pi epsilon naught r cube. This is inside. Electric field due to linear charge distribution is lambda by 2 pi epsilon naught r. So that contains E is inversely proportional to 1 by r. And the graph is like that. And sheet of charge is sigma by 2 epsilon naught if the sheet is a conducting charge, and depends upon sigma only. And for the sheet it is very interesting. The field is independent of the distance for the sheet. Electric field due to parallel plane sheets is, if these are having two positive charges or like charges, then field outside will be non-zero, field in between two will be 0. Of course here he has given that sigma A and sigma B different values. If both are having same, then in between will be 0 and outside will be non-zero for like charges. For unlike charges, in between field will be there, outside will be 0. Just you can draw the lines, that is positive charge will have always outward field, positive charge will have outward field, like the arrow marks like that, and you can check. Yeah, flux for this type of things. This is charge is in the cube, charge is in the cube inside, charge is in the cube, then flux coming out is equal to, second one I am telling first, q by epsilon naught, q by epsilon naught. Then flux passing through one of the phase is equal to q by 6 epsilon naught. Exactly the first case is, suppose a charge is at a distance some a by 2, then whatever the flux coming through this given side is q by 6 epsilon naught. And the third one is, charge is at one of the corner, then flux coming out from this body is 1 by 8 times of q by epsilon naught, and the flux coming out from the opposite side, one of the opposite side is q by 24 epsilon naught, and charge is on one of the face, then q by 2 epsilon naught, charge is at the one of the edge, q by 4 epsilon naught. Yeah, only fourth part belongs to the cube, that's why. Important results for field due to different bodies. Point charge q equal to kq by r square. These are all we know. Electrostatic potential and capacitance we are going to discuss from here onwards. In this lesson, we are going to discuss electrostatic potential, equipotential surfaces, potential energy of a system of charges, dielectrics and polarization, capacitors, capacitance, parallel plate capacitor, effect of dielectric on capacitance, combination of capacitors. First, we will see capacitor related concepts. Capacitance of a capacitor is C is equal to Q by V, it's a scalar. Capacitance of a spherical body is equal to a sphere of radius r, will have a capacity 4 pi epsilon naught r, and charge on positive plate of a capacitor is called charge of a capacitor. That means one of the charge magnitude only we are considering. Electric field between plates of the capacitor is sigma by epsilon naught, that is equal to q by a epsilon naught, sigma means q by a. And capacitance of parallel plate capacitor is C equal to epsilon naught a by d, when the space between the two plates is free. And series combination, charge is constant among all the plates, alternate positive negative will come. And 1 by C is equal to 1 by C1 plus 1 by C2. Potential difference is shared among them in the inverse ratio of 1 by C1 is to 1 by C2 and C3. Parallel combination of capacitors, potential difference constant, and Cp equal to parallel. So C1 plus C2 plus C3, and Q1, Q2, Q3 ratios are C1 is to C2 is to C3. Then number of plates n minus 1 are alternately connected. Then possible number of capacitors are n minus 1 into epsilon naught a by d is the equivalent capacity, of course. And then induced or bounded charge q dash is equal to q of 1 minus 1 by k. Capacitance of a parallel plate capacitor with dielectric of constant k and thickness T is given by epsilon naught a by d minus T plus T by k. When a metal placed between two plates, and metal means k value infinity, then obviously C is equal to epsilon naught a by d minus T. When dielectric is completely filled, C is equal to k times of C naught, k epsilon naught a by d. And the dielectric is filled with two slabs, dielectric constant K1 and K2, thickness T1, T2, then epsilon naught a by d minus T plus T1 plus T2 plus T1 by K1 plus T2 by K2. And when n dielectric slabs are placed completely, then by n will come, right, as usual. When different charges are placed, are given to a capacitor place, the charge on inner side of the plates is equal to Q1 minus Q2 by 2, provided Q1 is greater than Q2. And energy stored in a capacitor is half CV square. Energy stored in a capacitor is half CV square. And here I would like to tell you one more thing. Suppose here is one plate and here is another plate. This is given Q1 charge, this is given Q2 charge. Then Q1 plus Q2 by 2 will be here, and here also Q1 plus Q2 by 2, irrespective of their magnitudes. Then inside is equal to Q1 minus Q1 plus Q2 by 2. So this is going to become how much? Q1 minus Q2 by 2. That only here we get. And here reverse. Q2 minus Q1 by 2 here. So this is outside one. This is outside. This is inside. This is also inside. This is also outside. So outside charges will be same for a capacitor of different charges. Okay. Next, energy stored in a capacitor is U equal to half CV square. And energy density is equal to half epsilon naught E square. Energy density U is equal to half epsilon naught E square. Distribution of charges. Capacitors are connected in parallel such that positive plate of one capacitor is connected to positive plate of another capacitor. Then total charge will be added up C1 V1 plus C2 V2 by total capacity will be C1 plus C2. Then it will give you common potential. Total charge by total capacity, common potential. Potential energy loss in this case is half C1 C2 by C1 plus C2 into V1 minus V2 whole square. If one of the capacitor is uncharged, then V2 you can put 0, right? If positive connected to negative and negative connected to positive, then this case is positive connected. I think diagram is there, but I am drawing for my interest sake this one, and the other one is also given. The other one is positive is connected to the negative plate and negative is connected to positive plate. Then what happens? It is going to lose maximum charge. It is going to lose maximum loss of potential energy, maximum loss of potential energy, minimum. But never connect a capacitor after charging to another capacitor. Definitely rearrangement of charges takes place, then there will be a loss of energy. So here common potential is given by C1 V1 minus C2 V2 by C1 plus C2, and energy loss equal to half C1 C2 by C1 plus C2 V1 plus V2 whole square. Force acting on the capacitor plate is F is equal to half epsilon naught A square A. When a dielectric slab is introduced between the plates of the capacitor, then its capacity increases and battery is disconnected, then energy will be half CV square of K minus 1 by K. This is the work done, or energy change we can call. When battery connected, W equal to half CV square into K minus 1. The work done in introducing that what you call dielectric slab. When battery connected, potential difference remains constant and capacity will become K times, charge will be K times of Q naught, and E is equal to E naught, U is equal to KV naught. When battery disconnected, Q is constant and C is equal to KC naught, V naught by K is the potential and U naught by K is the energy stored. Next, and spherical capacitor with two radii A and B, then the capacity is 4 pi epsilon naught AB by B minus A. Cylindrical capacitor with radii A and what you call B, and the length L is given by C is equal to 2 pi epsilon naught L by log B by A with exponential logarithm. This is cylindrical capacitor. And capacitor resistance circuit in series combination, CR circuit we will call. Growth of charge is equal to Q is equal to Q naught of 1 minus e to the power of minus T by CR. E is equal to 2.7, of course exponential constant. T is known as T equal to CR, that is known as time constant. And important point is capacitors behaves as DC blockers after long time. And T equal to CR, time constant. Q is equal to Q naught of 0.63 after time T. After time constant this is. And while discharging, there is no 1 minus. Q is equal to Q naught e to the power of minus T by CR for discharging. And the charge after T seconds is equal to Q is equal to 0.37 into Q naught. This is growth of charge on a capacitor plate. And decay, this is decay of charge on a capacitor plate. And this is the circuit diagram for CR circuit, DC circuit. And these are all we discussed in the last sheet only. Repeated points. Next, force on a dielectric slab. Whenever you are trying to put a dielectric slab into the capacitor plates, it is pulled inside due to induced charges. That force is equal to epsilon naught BV square by 2D into K minus 1. When capacitor has constant charge, q square d into k minus 1 by 2 epsilon naught b into L plus x into k minus 1 whole square. This is constant charge process. This is constant potential difference. Constant potential difference means external source is present. Constant charge means external source is removed. Remember, when n identical droplets each of radius r are merged to form a big drop of radius r, then q dash, sigma dash, v dash, c dash, u dash are the respective things after the combination. Then capacitance and energy of the drop respectively. Then see, radius n to the power of 1 by 3 of small r, not y. This is r only. I gave by writing r, that I put like this. Q dash is equal to nq and sigma dash is equal to n to the power of 1 by 3 sigma. V dash is equal to n to the power of 2 by 3 v. C dash is equal to n to the power of 1 by 3 c, and u dash is equal to, remember, these two will be equal because capacity is proportional to r. That's why capacity is proportional to r, because capacity is equal to 4 pi epsilon naught r, isn't it? That's why. And remaining things you will get next. These are capacitor related things. Okay, end of this discussion. We will go with numerical problems in another session. Bye.